All right. Good. So before the break, we innocently wrote the gradient at some time t. I'm omitting the batch here. And we said this is the partial derivative of our error with respect to the parameters. But how do we find this exactly when we work with a deep, or in particular with a complicated neural network? Yeah, so we crucially need this to adjust the parameters. The large language models, they now have billions and trillions of parameters. And how do we find them? Well, by tweaking them so as to minimize the loss. And for this, we need these gradients. Now, in finding these gradients, historically, there have been a number of approaches. So what backpropagation is not, it is not numerical differentiation. So numerical differentiation would be to use, for example, finite differences. This numerical differentiation in linear parts of your, so where the loss changes linearly with parameters, this will be exact. But in nonlinear regimes, like if you have activation functions different from the ReLU, this would not give you the right result. And it's also not the same as symbolic differentiation, where you would have a purely abstract manipulation like Mathematica does, and you would then insert numbers only at the very end. What it is instead is the use of chain rule combined with dynamic programming. So maybe I should put a heart or something. You know, it's the marriage of chain rule and dynamic programming. And what it is a particular instantiation of reverse mode automated differentiation. Automated differentiation, or AD for short. Okay, and I'm mentioning that here because this automated differentiation is a mature field which was developed independently and also prior to machine learning, and then parts of it were reinvented here in the context of the training of neural networks. Okay, and we can start with a simple example. A multi-layer perceptron, and in particular one here, one which is strictly layered. So no skip connections, no fancy other parts. In particular, you know, we can take a really tiny neural network. Let's say we have two inputs. we have some nonlinearities. And we have a single output neuron. And then we can compare this output. This output we can compare to some ground truth label. And together this is evaluated in some loss function. And well, let's assume that we want to find those parameters from the first layer. In particular, there is a parameter here which I'm going to call 1 for the first layer and 1 for the first neuron and 1 for it's the connection between the first input and the first neuron. And well, a different way to write this neural network here would be to say that we have our input, which we transform linearly, and then we put that into an activation function A, and then we transform the result linearly with a weight matrix W2, and then we push that through another nonlinearity. So this was A for activation, this was sigma for this nonlinearity here, and then we have a loss function that depends on the true label Y and what we have just computed. Yeah, so this network I can write like so. And now we can look at this particular network. Okay, I don't want to copy everything here. We can look at its partial derivative with respect to here, this weight 1, 1, 1. All right. And now applying the chain rule, I can first differentiate my loss function with respect to this output of the neural network. And then I can differentiate my sigma, my output of the neural network with respect to its argument. And then I can differentiate that argument with respect to the activation function. And then the activation function with respect to matrix W1 times X. And then finally, the matrix W1 times X with respect to, okay, in full glorious detail, with respect to W1, and then dW1 with respect to D, and now finally comes my parameter that I want, W111. Okay, and this is the chain rule. And even this has been an abbreviation because the loss function itself, I have not specified what exactly it is. But it looks like so. Formally, yeah? And this will give us our gradient with respect to this parameter. Now let's look at the gradient with respect to the other parameter here. Namely, this multiplier here is from the first layer, it's from the first neuron, but the second input. All right, and now the first term is perfectly the same. And I'm doing this because I'm lazy. And the second term is also the same. And the third term is also the same. And the next term is also the same. And this term is also the same. And then this term differs. So here I need W1 differentiated with respect to W1, 1, 2. Okay, and just to emphasize it more, yeah, this here is the same. And that is the same. And that is the same, and so on. And now I did not copy it, but I just wrote these hashes because I'm lazy. And of course, when we do computations, we also want to be lazy. Yeah, we want to avoid duplicate work. And this means that all these parts here, we want to compute them just once. And this is part of what makes dynamic programming possible. Dynamic programming is possible under two conditions, and one of the conditions is that we have overlapping sub-problems. And it's clearly given here, yeah? These sub-problems, finding these parts here, that is the same in both cases. All right. Now, in principle now we have two different orders in which we could run these computations. Namely, we could start from the beginning to the end. Yeah? So we could evaluate first this, and then that part, and then that part, and so on. And this would be forward mode automated differentiation. Or we can start from the other end. We can first evaluate this, and then that, and so on. And this would be reverse mode automated differentiation. Okay, now there are a couple of things here which are interesting, namely, for example, here, this is a vector, and that's also a vector. And you remember we were discussing matrix vector calculus. So differentiating a vector by a vector will give us a matrix, or this could be a tensor, that could be a tensor. Then I would get an even bigger tensor that tells me how each of the element changes with respect to each of those elements. And in general, all of these entities here, these are Jacobians, telling me how the output changes as the input changes. And so all of these are matrices, and we can, in principle, thanks to associativity, we can decide in which order we want to evaluate all of those products. And in this particular case here, what we have is in this example here, that's a problem that's known as matrix chain multiplication. And now some of these tensors here can be quite large, but the loss typically is just a scalar. So the loss here typically is 1 by 1. So this is normally going to be a vector. And now depending on the structure of the network, it can make sense to multiply some of these matrices or some of these vectors before we multiply others. So in particular, if I multiply here a vector with a matrix, the result will be a vector. And then this new vector I can multiply with the new matrix, and the result will be another vector, and so on. So I never need to multiply two huge tensors with each other if I start from here. Yeah, so I have the reverse mode automated differentiation. That's one particular order where I start multiplying from the left. Forward mode is one particular order where I start multiplying from the right. And in principle, I can also have mixed modes. And in principle, for particular architectures, that could be advantageous. But normally, when we have multiple inputs and only one dependent quantity which we want to differentiate, it is most advantageous to start here in this reverse mode. Okay, now this writing down this chain rule and deciding what to do is easy as long as we have this strictly layered architecture. But as soon as we introduce skip layers or other loops in our computational graph, things become more complicated. I'm wondering if to stick with this example or if we should go straight to computational graph. All right, let's look at motives. Let's look at small motives first. So for example, if I multiply two numbers, let's say we have a scalar input and we have a scalar parameter, and we have a multiply operation. And let's take particular values. So let's say at the I want to now do a forward computation. So I say x equals 3 and w equals 7. Then in the forward pass, I send this information along my computational graph. This here is not an x, but it's a multiplication operation. But if I now want to, so what I have along this edge here is w times x. But if I now want to differentiate the result, I can, on the reverse path, I can say, okay, what's Wx differentiated with respect to Wx? The answer is 1. So I'm sending a 1 this way. And now at this point, I need to decide, well, this result here, dWx with respect to dx, we know is W. So the number that I want to send here is what I previously knew was holding. Namely, it was this 7. And here I'm putting this above the arrow, excuse me. So I was pushing the 7 this way in the forward pass. And then we have the backward pass. All right, here in the backward pass, I need to know that dWx with respect to dW is x, and x was 3. So this time I am sending a 3 in this direction. So now I have computed my gradient of the output with respect to x and w. The numbers are 7 and 3 respectively. But to do so, I needed to remember what were the results in the forward pass. And these results, so these numbers that we were sending in the forward pass, the numbers that we were sending, they're also called primals. And now, if you imagine that we have a deep network, so let's say there's lots of stuff going on before we even get to this point, then if we now want to propagate the gradient back, it would be inconvenient if we had to recompute, well, what was the contribution of this arm and of that arm? Yeah, and hence these primals are tabulated in the forward or during the forward pass. In reverse mode automated differentiation or in backpropagation. All right, but I'm not always so lucky that this result, W, that I have some input and some input. I'm not always so lucky that I'm producing just a single output. Sometimes I'm producing several outputs. Maybe this is going to be a skip link, or maybe this goes straight to the loss function, or whatever, depends on the architecture. Yeah? So what we need is a directed acyclic graph. Or DAG for short. And in this directed acyclic graph, what we need to remember during the forward, or what each node needs to know are the primals that went in. And the node needs to know how its output is differentiated with respect to the input. So what primals went into it? Which children it has, in the sense of the directed acyclic graph. And it needs to know its the derivative of its output with respect to its input. So here, this was a multiplication operation. So in order to send the right information back, we need a prescription of how to compute the derivative of the output with respect to each of the inputs. And if we create a new operator in PyTorch or a new operator for autograd, we can define what's happening in the forward pass. So what does this operator do with its inputs? And we also need to specify, and that's usually the result of an analytical computation, what's the derivative of the output with respect to the inputs? All right, and if we now use this kind of motive, but if we generalize it, we come to a scheme that looks like so. So we might have any number of children here. So on. And we are interested in the partial derivative of node number I. We are interested in the derivative of the final loss or the final outcome with respect to a particular node. So what we want is that the partial derivative of some output, like the error, with respect to a particular, so Vi is just here for vertex I, with respect to a particular vertex in the graph. This is what I here wrote as Vi bar, following the notation in the automated differentiation literature. And so in a setting of a simple chain like this one, I could formally write this as, here we have our loss with respect to, let's say this would be VL for layer number L times the derivative of VL to VL minus 1, and so on. And here at the end, we would have And now we can, somewhere in between here, we will have d vi plus 1 with respect to dvi. And this entire thing here, I can summarize as this would be dl by dvi, or vi bar for short. Okay, so this is now the example we had previously for the multi-layer perceptron, written in this notation here of various vertices. But here we had a simple chain of operations, and in general, when we have skip links or other more complex neural networks, we might not have a simple chain. And then we need to look at what gradients we produce downstream in the computational graph, and then we will send them upstream in the computational graph. All right, so what we need here are the partial derivatives. So this would be dvj with respect to dvi. And then I can compute vi bar as a sum over its children. So j are now all children of node I in the directed acyclic graph. And then we have dvj by dvi times the gradient that we had found at those children. All right, and this quantity here, that's a local gradient. And this local gradient that typically requires primals. And we have the gradient that we are going to send backward. These are also called the adjoints. Yeah? So this property here would be the adjoint at node I. So this was the derivative of our final outcome, the error or the loss, with respect to the operation defined in node I. Okay, and this we can now, this recipe, we can now apply to computational graphs of arbitrary complexity. If we want to come back to this particular example here, we can try and build this computational graph. So we had the inputs x1 and x2. And then we multiply x1 with our parameter w111. So we have a multiplication operation. And we multiply x2 with w112. That's a multiplication operation. And then these two are summed up. And put into a nonlinear activation function. So let me write A instead. A for the activation function. This would be the output of the first perceptron. And now for the second perceptron, I have a parameter W first layer, second perceptron, first input. And it is also multiplied with X. I need another parameter, first layer, second perceptron, second input, another multiplication. And then these are also summed up. And put through nonlinear activation. So that would have been the computational graph of my first layer. And then I need more parameters for second layer, first perceptron, first input, second layer, first perceptron, second input. I again multiply these. I add them up, and I send them through some nonlinearity, sigma. And then I compare this to my desired output by means of a loss function. And here I'm writing just L, but this is a shortcut. L in itself would be another computational graph. Yeah, so if I did take squared loss, then I would have to take one minus the other and then send it through a squaring operation and so on. Yeah, and this here would be my error of W. Okay, so this tiny neural network gives me already this large computational graph. And this is what happens in backpropagation in general. So pseudocode for backpropagation would be that's a very, very high level pseudocode, which I'm giving here, would be to build the computational graph. And this can be done either statically, as the early versions of TensorFlow did, or it can be dynamically, as PyTorch did. If you build it statically, you have more options to try and optimize your graph automatically. If you do it dynamically, you have more flexibility in making the computations depend on intermediate outcomes. Then you run a forward pass and you store or tabulate all your primals. And that means that we need a lot of memory. So this is why to train a given neural network, you need much more RAM than to run it later. Because during training, you want to do backpropagation, and then you need to store all the intermediate values. If you don't want to store all the intermediate values, because it would really blow up your memory consumption, then you can also have let's say if you have some really deep neural network, then you can also store your intermediate results or your primals only at a few points, but you need them everywhere, right, to route the gradient backwards. And these would be called checkpoints. And then at the expense of extra computation, you can then recompute your primals from one checkpoint to the next. Yeah, so this allows you training models that otherwise are too large to fit into your GPU or your computer to run backpropagation. All right, then you need a topological sorting of your DAG. So here this result always depended on the children. So I can only compute the adjoint at node I if I already know the results, if I already know the adjoints at all the children. And so this topological sorting gives me an order for the executions. And then finally, starting from the last node, we start propagating the gradient backwards. And this is now, you can look at it in terms of message passing in your computational graph. Yeah, so you propagate messages backward from your loss to your intermediate computational nodes in the graph. And the result is within machine precision. The result is exact because we have always used, so each node needs to know how to compute the partial derivative of its output with respect to its inputs. And this needs to be coded, this is hard coded for each node. And if this formula is true, or if this formula is correct, then it is applied with specific numbers that you get from that you get in the course of your backpropagation. And if we look at this tiny example here, so we had an input 3 and a parameter, or let's say we had these two inputs. We produce an output of 21. If 21 was either too little or too much, then the gradient tells us, how strong is the benefit of changing either this, if this was a parameter, then this would tell us how strong is the benefit of either changing this parameter or that parameter. And here for a multiplication operation, interestingly, the benefit of changing this parameter depends on the value of the other one. So if we think that the output 21 was too small, then by the numbers that we propagate backwards, here we propagate back a 7, and here we propagate back a 3, we see that we have more leverage, or if we do a gradient descent, if we change our parameters iteratively, we have more leverage if we change this one than if we change that one. And this is why we need to store the results of the forward computation so that we can, on the way back, adequately distribute the gradient that comes from the end of the computational graph to its roots. By the way, the result looks very different if we have a plus here rather than a product, because then both children, or here both ancestors, contribute equally. Okay, so the result is exact, and the resources we need approximately twice the memory twice the compute and yeah, I think we can also say approximately twice the memory. If we say the other part, so one part of the memory is needed to store the parameters, and we need around that amount of memory also for the primals. Need approximately twice the compute and memory for backprop. Relative to inference, when we just run our neural network with a fixed set of parameters for a given input. Okay, so on the one hand, it's just chain rule. On the other hand, it took people quite a long time to figure this out correctly. So it took until the early 80s. So often Verbos and Rommelhart, who both published papers on this independently in 1982, often they are credited with inventing it. And this is what made the training of deeper neural networks as we use today possible in the first place. And now that we know how to train these things, we will move to more interesting architectures in the next weeks, looking at, on the one hand, convolutional neural networks, but also graph convolutional networks, graph neural networks, and then attention and transformers and so on. These will be the massive architectures that we build, but the way of training them is always the same, and it's encapsulated in this picture and in this formula. Thank you very much. Have a good week.